Hi, this is Hariom. In this talk, I'm going to talk about our work on spatio-temporal multilevel strategies for image registration. This is a joint work with Professor Jan Motszewski from University of Lübeck, Germany. I will start with a very brief introduction on image registration approaches for more than two images and existing multilevel strategies. I will then point out the advantage of multilevel schemes and then discuss about the proposed spatiotemporal multilevel strategy. This strategy has mainly three ingredients: the discretization of the spatiotemporal space, the interpolation methods, and the stopping criteria. Afterwards, I will show the effectiveness of our proposed scheme on four-dimensional optical coherence tomography dataset of a human eye. Then we will conclude our talk and point out the ongoing work on this topic. In this slide, you see the two video. These are the OCT scan of a human eye. During the scanning, the eye movement is not stable. Therefore, you see a lot of fluctuation on the left-hand side video. In this scenario, image registration comes into the picture where we want to stabilize these high fluctuations in these scans. And because of correction, the doctors can easily see the blood flow along the RP layer in the human eye. So after a registration, we obtain a stable image. As you see on the right hand side, the most of the major fluctuations are easily corrected. So in image registration, here we want to align more an image sequence. So we want to find out the deformation map such that if we apply the deformation map on the image sequences, all the images look similar to each other. So in order to find out these deformation maps, we are using the variational framework based registration models. It consists of mainly two parts: the similarity measure D and the regularizer S. Similarity measure measures the similarity between the images, and in this work we are using the Pearson correlation coefficient. The regularizer incorporates the prior knowledge about the deformation field. So for an example, in order to enforce the local smoothness, one can penalize the first order or second order derivative of the transformation field. So irrespective of your similarity measure or a regularizer, most of the registration models for medical images are highly non-convex. That means they have many local minima. In order to illustrate this behavior, I am taking the two images here, the R and T. The T image with respect to the R image is slightly translated along the horizontal direction. So T of Y will show you the translated version of the template image, and then on the right hand side we will plot the objective function D, which just simply calculates the similarity between the translated image and the reference image. So as you see here that this objective function has a lot of local minimas like this one, this one, this one, and this one. And this is our global minima. So it might be possible that if we start from this location, our registration algorithm stops at this location and we never is able to reach to the global minima. So in order to avoid this local minima in image registration, we mainly use the multi-level strategy. So multi-level strategy is mainly consists of a few steps. So what we do here is that we smooth the given images, we discretize them at the coarse resolution, and then again we smooth the image and discretize at another resolution. Then we solve the image registration problem from the coarse to fine resolution. In order to illustrate this behavior, I am taking these two images, R and T. We smooth the images and then we discretize by a factor of 4, and this is how we build up from left to right or build up a hierarchy of the images. So as we are going from the left to right, the images are getting smooth and represented at the coarse resolution. On the right hand side, you see the objective function plot corresponding to this image set. So as we observe that the red is corresponding to the finest image, the image at the finest resolution, and the green is the image at the coarsest resolution. So as you see here that because of the image smoothing, the objective function is also getting smooth. So you do not observe these local minima which is present at the final resolution also at the lower resolution. So what we do is, because of the so that's the one of the point which want to highlight here, is that because of the image smoothing, our objective function is also get smooth and it reduces the load of local minimas. The next important point here to highlight is that, so we start with the registration of the images corresponding to the green curve. So we get a good estimate here, and then we use this as an initial estimate to optimize the images at the registration problem at the higher resolution. So because of this good outstanding initial guess, we need very few iterations at the final resolution, and that's one of the primary reasons that we can accelerate our registration process. Now the question is how one can design a multi-level strategy for more than 2 images. So like as we saw earlier that we have a video, so we have an image sequence. So one of the simple strategy is just to extend what we are doing so far for the 2 image case. So here the x1 and x2 represents the spatial direction, and the time is represent the temporal direction. So in this strategy, what we are doing is we are just simply discretizing the images. So we do not perform any discretization along the temporal direction. So we first perform the registration with the 2x2 image, then 4x4 and 8x8 image for an example. So in this strategy, the shortcoming is that we do not exploit any temporal smoothness which are intrinsic to these image sequences, and that's what we want to focus here in this work. So before going further, I want to explain what do we mean by the temporal smoothness. So what you see here is that as we saw earlier the OCT videos, I'm plotting one of the component of the transformation field here over the time. So you see the translation along the z direction in that video. So as you see here, this translation parameter is smooth over the time, and these images are corresponding to a part of this temporal domain. So I'm plotting the images from T24 to T31. We observe that all these images are highly correlated, and the transformation field is not varying too much. So what we can gain from here is that if I know the transformation field at T24 and T31, I can approximately guess the transformation field in between here because of the smoothness of the transformation field. So how we do that here? So let's suppose I have 57 images in this case, the red curve what we want to estimate. So instead of registering all the images together, we start with the registration of only 8 images, and that's what gives us the estimate, which is given by this blue circles here. Now what we do is we do the linear interpolation for the images in between these circles, and use that dotted line or that initial estimate to register all the other images. Because this dotted line gives a very good initial gap, we can accelerate our registration process. So our spatio-temporal strategy consists of mainly 3 parts: the discretization of the spatio-temporal space, the interpolation methods to interpolate the transformation field along the temporal and the spatial dimension, and we will point out that it needs a spatial care. So we cannot simply perform the linear interpolation at each level. And the third thing is the stopping criteria, which is very important to reduce a lot of computation time. So how we start with is, so as you are going from top to bottom, so the top, the spatial discretization is increasing. So we start with the 2x2 image, then we go for the 4x4 image, and then we go for the 8x8 image. From left to right, we define our temporal discretization. That means we start the registration of 3 images, then we go for the 4 image, and likewise we increase the number of images in each discretization level. The arrow indicates the sequence of registration. So that means we start with the courses spatial level and the courses temporal level. We first register the 3 images, we get an estimate, we do the interpolation, use that as an initial guess for the next level, and then we register 4 images. And likewise it continues. After registering all the images in the coarsest level, we get an estimate which we call YL, and then use that estimate at the fine spatial level. Here the interpolation is different for the coarsest level and the spatial level. So we perform the linear interpolation only on the coarsest spatial level. We will explain why we are doing that and why we need a special scheme when we go from the coarsest to the fine spatial level. One of the important thing to note that right now we are doing interpolation component wise. That means if in the OCT case, mainly we are focusing on the affine deformation. So for the 3D data set, we have 12 components. So we interpolate each component independently over the time. So at the courses level, so we start with the first registration of 3 images. To register these 3 images, we initialize our registration algorithm with the identity map. So identity map simply means that we assume that there is no deformation. And after the registration, we get an estimate eta. So in this plot, the eta is represented by these black circles here. Now we need to build up an initial guess to register these 4 images. So what we do simply that we linearly interpolate these 3 dots. We get an estimate for all the other images. Then we use that as an estimate initial guess to register the 4 images, and this continues. And at the end, we get the estimate YL, which is represented by the red curve here, and that we use for the next spatial level. So the red curve is what we have computed so far from the coarse spatial level, and that's the initial guess to register these 3 images in the next and at the final level. So now we register these 3 images, we get an eta. So because of the final resolution, your estimate may improve. So that is why you see a shift for these 3 images. So these black circles are the new estimate at the final resolution. Now in order to build up an initial guess zeta, one can simply do the linear interpolation. But if we use the linear interpolation, we are simply discarding a lot of information which we have computed for the other images at the coarse spatial level. So we need a better strategy to utilize that information. So in order to do that, we solve a linear least square problem. This is the first part of the linear least square problem, simply trying to manage that we want a new estimate which is close to the estimates computed already at the coarse temporal level. And in the next part, we are simply saying that we want the first order derivative of our estimate close to the first order derivative of the estimate which we have computed at the last spatial level. So our interpolation scheme at the all temporal level provides a estimate for all the images in the sequence, and that allows us to compute the distance measure using all the images. So at each temporal level, we can compute the distance measure for all the images, and if we observe that the distance measure is not changing from going from one temporal level to another temporal level, we can stop beforehand. That means that you don't need to register all the images at in any point of time. So in order to solve the effectiveness of our strategy, we are performing the registration of a 4D OCT dataset. We are mainly focusing on the affine deformation, which seems to be good enough for this dataset. In order to measure the similarity, we use image intensity as a feature. We have 129 images. We define 4 temporal levels. So we start the registration with 17 images. Then we go for 17 to 129. So we go for 17 to 35, then 65, and then 129. We define the three spatial levels. We compare our strategy, which we call the STML, to the state of the art spatial multi-level strategy here. So you see the first left hand side image is the unregistered image. So it's a 2D image from the 3D 4D space. So the horizontal axis is the time axis and the vertical axis is the line in the 3D space. And because of the because these images are not registered, that is why you see the profile curved profile here. And after registration, these are quite nicely aligned from both of the methods. So we do not observe any difference in the quality from these two methods. But there is a significant difference in the speed up. So we are comparing here the two data sets, so D1 and D2. So as you see here, the total runtime from the our proposed scheme only taking 200 seconds, and from the other method it's 540 seconds. So we observe a speed up of around 2.8. And for the second data set, we also observe a speed up of around 2.5. Now we conclude our talk. So we propose a spatio-temporal strategy that exploits the temporal smoothness. We are also building up a suitable interpolation methods that provides a smooth temporal transformation field, and we accelerate the registration on the OCT dataset by a factor of 2.5. The ongoing work is mainly focusing on using these strategies for PET and MRI datasets. We are building an interpolation scheme which gives a diffeomorphic transformation field for non-registration, and also investigating the image smoothing along the temporal dimension. Thank you so much.